volume is going to be equal to, and this is the disk method, it's going to be equal to pi times the integral from a to b of our radius, and our radius is going to change for each disk unless it's just a straight line, squared dx. So it's kind of like pi r squared, and then the dx is the width. It's dx. If this is in terms of x, this is in terms of x. Alright, so as long as we have a horizontal axis of revolution, that means what you are revolving about is a horizontal line. Then we want to set up we want our equations to be y equals x, and we use x intersection points. That's what A and B stand for. So here's a picture, and you don't have to draw this picture, this is in your book. But here's a picture of in general, if we have a horizontal axis of revolution, what we're doing. You know, and then of course it's going to become three-dimensional. Whenever we revolve. But if we have a vertical axis of revolution, well, what am I talking? Horizontal means that where you're revolving about is a line that's from left to right. Because if I don't revolve about a horizontal line, if I was to take this and try to revolve it about a vertical line, the same y equals x equations. What am I talking about? And I'm going to erase this so you don't have to copy this down. But let's say I was revolving about this line. This is a vertical line. This no longer is a disk. Think about the shape that it would make. There would be a distance from here to here. This would go around. This would go around. You know, it would come back around. It's hard to draw in 3 dimensions. You know, but it would be a what? What do we call that kind of shape? And I kind of butchered it, but it would be a cylinder, or what your book would call a shell. And we actually go over the shell method, summing up an infinite number of shells rather than summing up an infinite number of disks. But first we're going to do the disk method. Okay. And so as long as we have a horizontal axis of revolution, when we revolve a vertical rectangle, it will form a disk. If we have a vertical axis of revolution, then with the disk method, we don't want y equals x, we need x equals y. Okay? And so our volume is pi times the integral from c to d. Anytime you see c and d on as the upper and lower boundaries of your integral, upper and lower limits, that means those are y values. That's generally what we let those stand for. Okay? And then it'll be of r of y squared dy. That's if we have a vertical axis of revolution. So think about it. If we have a vertical axis of revolution, which way is the rectangle going to have to be turned? It can't be vertical. if you are revolving about a vertical, because that won't give you a disk. It has to be just the, I guess you could say the opposite, right? If you're going about a vertical axis of revolution, then your rectangle has to be horizontal to form a disk. That would form a disk, right? You got to imagine it going around, all the way around that vertical axis, vertical y-axis, or just a vertical line in general. Now, with either one of these, we've got to be able to figure out the radius of the disks that are being formed. Notice that depending on where you are under this curve, the radius of the disk or the height of the rectangle is going to change. And it's going to change depending on what curve this is. And this will be like our f of x. Right? And so wherever I am on f of x, if I'm right here, then the height of my rectangle will be that. Now if I'm right here, the height of my rectangle is that. So the height of the rectangle changes depending on the curve. But if we have multiple curves and it starts looking kind of confusing, remember we can always say top curve minus bottom curve. Alright, top curve minus bottom curve if it is a vertical rectangle. And what can we always do to find the height of the rectangle if it's x equals y? You can say right curve minus left curve. So if it's not an axis that we're revolving around, if it's an axis, you're saying right curve minus 0 or top curve minus 0. But if it's not an axis, if it's an actual line somewhere, then we may have to say the function minus 1 or the function minus -1 or something like that, depending on what we're revolving about. Okay? Let's look at an example of a disk method problem. And don't freak out just because you see a trig function, because it really doesn't have that much to do. I mean, it has something to do with the problem, but it doesn't make the problem hard at all. If you can integrate sine and cosine, you can do this problem we're about to do. Which hopefully you can. All right. So this problem says, let's find the volume of the solid formed by revolving the region bounded by the graph of f of x equals the square root of the sine of x. And then we need something else. We need some other boundaries. So I didn't copy them out, but I'm going to write them out. And the x-axis, where x is greater than or equal to 0, less than or equal to pi. About the x-axis. So we're going to revolve this about the x-axis. Alright, so first we need a rough sketch. Remember, we can't get out any negative values when you have the square root. So think about the way the sine curve looks between 0 and pi. That's something we should all know. Here's pi over 2, let's say right here. And here's pi. And so we start here. We know that we have a high point, or sine is equal to 1 at pi over 2. Then it's equal to 0 at pi. So this is, we're taking this part of the sine curve. And it shouldn't be exactly semicircular. It should be a little curve to it, I guess. But we're going to take that and we're going to revolve that region about the x-axis. So that's a horizontal axis of revolution. So what we're doing is we're going to take an infinite number of these rectangles. I know I'm putting space in between mine. But imagine if I could draw, you know, 1,000,000 rectangles in this little small place. Right? Not even that. I mean, more than that. That's just a drop in the bucket. And I sum up an infinite number of those, then I would get the actual area of the three-dimensional object that it would form. So what would the three-dimensional object look like? Kind of like maybe a lemon or a football or something like that. Here's a better picture of what it would look like, you know, after you revolved it all the way around. Alright, but we're taking little pieces and summing up the area of all of those, or the volume of each one of those little pieces, and getting the actual volume. Okay. So our formula, if we have a horizontal axis of revolution, which we do, because it says about the x-axis, that's a horizontal axis. Our formula is volume equals pi times the integral of the radius of the disk squared dx. Alright, and we need to know how to find the radius of each disk, which is the height of each rectangle. So we say top curve minus bottom curve, or it's just actually going to be this curve right here. That's going to be the height, depending on where we are on that curve, will give us the height of each rectangle. Alright, so the thing that I'm going to be squaring in here is the function. The square root of the sine of x. And then what are our boundaries? What are our x intersection points? 0 right here to where? Pi. Alright. So let's square sine of the square root of the sine of x. So that's just going to be the sine of x. Alright, so, and we have a pi in front, and we're integrating from 0 to pi. So what's the integral of sine? Negative cosine. So I do have a pi in front, and then I get negative cosine of x, and I'm going to evaluate that from 0 to pi. So I have a pi in front, I'm going to leave it in front, and then I'm going to plug in pi, plug in my top boundary, that's negative cosine of pi, minus, plug in my bottom boundary, negative cosine of 0. Alright, so what's the cosine of pi? Negative 1, right? So it's the negative of negative 1, just 1. And then I have minus negative, so that becomes plus the cosine of 0, which we know is 1. So it's plus 1. So the volume is equal to 2 pi cubic units. I don't know what the units are, but it would be 2 pi cubic units. Now on this one, we didn't have to say top curve minus bottom curve, right? We didn't have to say top minus bottom, but we really did. It's just that the bottom curve was 0, so it didn't do anything. When we start to revolve about something that is not one of the axis, then we are going to have to make sure we say top curve minus bottom curve. All right, let me show you what I'm talking about. So let's say that I wanted to find the volume. Formed by revolving the region bounded by the graphs f of x equals 2 minus x squared, g of x equals 1, about the line y equals 1. All right, let's see how good we can sketch this. Let's just do a rough sketch. I know I could just show it to you out of the book, but if you're going to have to do this anyway, you might as well get a little practice. And we're not going to be exact here. You know, anytime we need to figure out intersection points, we can just set equations equal and solve, or do something like that. Alright, so where is, or what is f of x equals 2 minus x squared? We know that's going to be a parabola, or quadratic, right? It's going to be opening down, excuse me, downward. How do I know that? Because of the minus in front of the x squared, that tells me the parabola is opening downward. So remember how to find x-intercepts and y-intercepts real fast. To find x-intercepts, you set y equal to 0 and solve. To find y-intercepts, you set x equal to 0 and solve. I would think the easiest thing to find here would probably first be the y-intercept, because you just set the x equal to 0, and so you get y equals 2. Alright. So I know it's going to touch here, and I know that it's going to be opening downward. What if I wanted to find the x-intercepts? I'd set y equal to 0 and solve. So what would I get if I set y equal to 0? I'd get x squared equals 2, right? All I'm doing is setting this equal to 0 and solving for x. So x squared equals 2. So x equals square root of 2, square root of negative 2. I have no idea. I mean, I know it's about, I think it's about 1.4 something, just because I teach math. So I'm just going to just guesstimate, because this is all just a rough sketch, right? I'm just going to guesstimate that that's right there and right there. So I know that that's what that part looks like. Now let's graph g of x equals 1, which is basically just y equals 1, and make it a different color. So go to where y equals 1, put a point, and then draw a horizontal line. Okay. So that is y equals 1. And then we're revolving about the line y equals 1. Which is, you know, it makes it a little bit easier that we're revolving about a line that's at the bottom of our curve, or the bottom of our figure. Because we're talking about this region here, right? This is where all of my rectangles are going to go. Alright, and I'm going to sum up an infinite number of these rectangles, but I'll be making these vertical rectangles like that. Now, to get the height of each one of those rectangles, this is one where I'm not going around an axis. I'm not going about the x-axis. I'm still revolving about a horizontal line, though. Horizontal is left to right. So I still want all my equations, y equals x or f of x equals x. But to get the height of each one, I might have to say the top curve minus the bottom curve. So in my formula, my r of x, the radius of each disk that I'm going to make, is going to be the top curve, which is 2 minus x squared, minus the bottom curve. What's the bottom curve?
1.
Just 1, right? Because this is where I'm revolving it. Top minus bottom. All right, so let's see. 2 minus x squared minus 1. What is that? Put the 2 and the negative 1 together. You get 1 minus x squared. So that is the formula that will give me the height of any rectangle. What would this figure look like? Again, I think it would kind of look like a ball. My drawing is not the best. I'll show you what the book says that it looks like, because they have all their drawings done with usually Mathematica or Maple or something like that. It's a lot easier to work with. I think it's actually stretched down a little bit more, but it would look something like that, kind of like a lemon or whatever you want it to be. And so what we're doing is we're finding the height of each one of these rectangles. And notice that the bottom is at 1, so that's why we have to say the top curve minus the bottom curve. Because if we didn't, the height that we would get, say right here, would be 2. But it's not 2 units from here to here. It's just 1 unit from here to here. But if we said 2 minus 1, we would get that 1. So that's why we're saying top minus bottom. Okay? Well, let's plug this stuff into our formula and work our problem out. All right, so our volume formula for the disk method is pi times the integral of. Now we need that radius of each disk. That was 1 minus x squared. I got to square each one of those. Or I got to square that term, sorry. Dx. Now I need my boundaries. I need the places where I'm going to integrate from and to. Alright, so if I go from square root of negative 2 to square root of 2, here's the square root of negative 2 right here. So you're saying I'm going to sum up all of this, then all the way over to right here. So I'd be having a lot of extra stuff. So what we need to do is we need to figure out what x value is this right here, and what x value is this right here. And anytime we want to figure out x values and we have equations, we set equations equal. If you set them equal and solve, you'll get the intersection points. Okay, so which equations am I talking about? I'm talking about this red equation, the 2 minus x squared, set it equal to y equals 1, or g of x equals 1, because they're both of x. They're both y values. So we set this one equal to this one and solve. That'll give us these x values down here. So 2 minus x squared equals 1. It's a quadratic. It's an easy quadratic. Right? Because if you move the x squared over and then move the 1 over and flip it around, you get x squared equals 1. Take the square root of both sides. You get x equals what? Plus or minus 1. If we just go 1, we just have one boundary, right? Yeah. So when you take square root, you got to make sure you put a plus or minus in front. All right. So these values here, these are these x values here on the x-axis. And so that's the boundaries for my integral. Once you set the problem up, then it's just up to can you do the algebra and the integration. You know, but you got to have a good sketch to be able to set up a good problem. Now, how do I square something in parentheses? This is one of my biggest pet peeves in math. When you have two terms, a binomial, and you're squaring it, you never just square the first term and the second term. If you do that, you're going to trigger me, and I'm going to like go crazy on your paper. So we never want to, if we have a binomial, we never want to just square each term. You have to write down the binomial twice and multiply it out. Some people like to call it foiling it out. It doesn't matter as long as you understand. It doesn't mean square the first term and square the second term. All right, that's not going to work. That's just one of my pet peeves in math. So multiply that out. You'll get 1 minus 1x squared minus 1x squared. So right now I'm not doing calculus. I'm just doing algebra. We said 1 minus 1x squared minus 1x squared is minus 2x squared. And then what's negative x squared times negative x squared? Positive x to the fourth. So now we've done our algebra part. Now we can actually do our calculus part. We can integrate. Don't forget the integral of 1 is what? X. Alright, I brought down my pi too, don't forget that. So it's going to be x minus 2/3 x cubed plus x to the 5th over 5. And then I'm going to evaluate that from -1 to 1. Alright, so plug in a 1. We have 1 minus 2/3 plus 1/5 minus, plug in a -1. I got to be careful here. So that's -1. And then when I plug in a -1 right here, that's going to be a -1 times the -2/3. So it's going to be a positive 2/3. Then I plug in a -1 here. I'm raising it to the 5th power, so it's going to be a -1. So it's going to be minus 1/5. And how do I know that to the 5th power, how do I know that's going to be a -1? Because it's an odd power, right? It's an odd power. And you plug in a negative value, you get out a negative. If it's the even power and you plug in a negative, you get out a positive. I don't know. What's the answer? Let's see. We got, I'll put that over 15. So I have 15 minus 10 plus 3. Do y'all understand what I'm doing when I do this little fraction right here? Yeah. Some people don't. It's a lot easier than just making like 3 of them. You just like, make 1 and then, okay, I'm going to do a 15. And so that's -15, and then that goes in there 5 times 2 is plus 10. And that goes in there 3 times -1 is minus 3. Especially if you don't have a calculator to do it, it's just a little easier to do it like that. So that's pi times 5 plus 3 is too big of a number for me to comprehend. 8 over 15 minus -8 over 15. So 16 over 15 times pi cubic units. Alright, so the second part of this section, I'm just going to introduce it, then we're going to take a small break. The second part of this section is still considered to be the disk method. It's just a special case of the disk method. So what this special case is is if you have a rectangle and you're revolving about a line and you have a little space here in between the rectangle and the line. Alright, we still have a height here, so that's still considered to be our capital R. But we're going to have a little piece here that's going to be missing. We're going to call that our lowercase r. So capital R is going to stand for our outer radius. And actually, it won't be just that little piece. The capital R is the whole thing. So that's the height of the rectangle all the way down to where you're revolving. And then the piece that's missing there, that's our little r. That's going to be called our inner radius. Now I want you to, and then of course we have a width. That's going to end up being our dx. I want you to picture what that would make if you took that rectangle and then you had a little space and you revolved it all the way around. Donut. That's what I like to hear. I mean, it's not mathematically, usually you don't call it a donut. They call it a disc. Or not a disc, but a what? I know. One person should know. A washer. Yeah, so it's just like a washer. If you put stuff together, one day you're probably going to have kids and you're going to get so mad when you're putting that swing set together because you're going to have like 90 washers that you have to put on there, and then you're going to forget to put them in the wrong places. And all right, so it's called the washer method, and to me it kind of looks like a donut. But what you're doing is you're basically finding the volume of the whole thing by using big R, and then you subtract out the volume inside by using the little r. So whenever you set up your integral, it's a very similar formula. It's just we have to subtract out the inside piece. So we're finding the volume of the whole thing with the big R, and then we're subtracting the piece out here with the little r. So volume is equal to pi times the integral from a to b of capital R of x squared minus r little r of x squared dx. Alright, and capital R of x, when we're working problems where we're missing stuff inside, that is the outer radius, and this is the inner radius. Alright. So we're going to take a little break now. Earlier we were revolving about a line and there wasn't any space, right? So this line y equals 1 or g of x equals 1, there was no space when you revolved, so it didn't have a center or a piece that was missing. But if you have a piece that is missing like this, and it's not always just going to look like a, just like a disc, exactly like a disc, because it's going to depend on all the other lines. But it's different. It's because we have to do the volume of the whole thing, or if you want to say the area really, but then we're saying at times the width, so that makes it the volume. And then we're subtracting out the volume of the middle piece. So because when we revolve it about the line, you're missing some stuff. So let me show you a problem where we could revolve about a line and be missing some stuff. This WebAssign being crazy, so I gotta pull the book back up. just a second. This takes a while sometimes. So funny, 20 years ago this would have taken like the whole hour to pull up the book. Whenever I first had the internet here at Colin, had to dial in through to Jackson to get it. No, it wasn't very fast. All right, so before we work a problem, let me just show you what the figure would look like. So we're going to have, most of the time we're going to have two lines that are going to intersect somehow, like the one here on the left. We figured out how to find the area between those two. But what if we want to take and revolve this region? Almost looks like kind of like a banana or something. We want to take it and revolve it about this horizontal axis. But when you do, it's going to have some thickness to it, kind of, here in the middle as it gets revolved around. On the edges, it's just going to be like a rim, kind of like a rim there on that side and on that side. I guess if it didn't have a lot of thickness here, it would kind of remind me of like one of those dog collars they put on the dogs so they can bite themselves or something. But the main thing is that you're missing some stuff, and so we figure out the area, the volume of the entire figure by using the outer radius, the big R of x. And then we subtract out the inside missing stuff. That's the inner radius, the little r of x. Okay, the formulas are the same, except we have capital R of x squared minus little r of x squared. So let's see this in action. Let's find the volume of the solid formed by revolving the region bounded by the graphs of y equals the square root of x and y equals x squared about the x-axis. Alright, so let's just throw down here. Let's throw down a rough sketch. It's not the exact. Should have kind of a basic idea of y equals the square root of x, what it looks like. Think about it, as your x gets larger, your y is going to get larger, but it's not going to get larger as fast. So like if x is 0, you get 0, but like, and x is 1, you get 1, but then if x is 4, you only get 2 for y. X is 16, you only get 4 for y, so it slows down. It doesn't go up as fast. So it kind of goes out like this. All right. And then we all know what y equals x squared looks like. That's our parabola or our quadratic equation that starts here at 0 and kind of goes up like that, and kind of goes up like that. It's supposed to be symmetrical on both sides of the y-axis, but whatever. It looks good enough for me. And so what we want to do is we want to take this right here, all these rectangles here. And then, you know, we got some missing stuff in there too. But we want to take that and revolve it. It says about the x-axis. So whenever we revolve that thing around, it's going to kind of look like that, you know, that, I guess you could say that dog collar or whatever you want to call it. It's going to look kind of like that. Maybe your ice cream cone there with no bottom. Yeah, just a cone. I asked my daughter the other day, she had one bite on her ice cream cone left, and I was like, why don't you give me that last bite? And she just looks at me and just... She's only 8, so... I should have took it from her. Anyway. Alright. So we want to revolve this thing about the x-axis. We're missing some stuff inside, and we know, you know, it's going to form this shape, and it's going to have some thickness inside of it, and it's kind of hard to draw in 3 dimensions. But it's going to have this thickness. We wouldn't be able to see this part, but then when we get to the edge, it's not going to be as thick. It's going to make like a rim there. Okay. Ours actually touched right here at the origin, so we are going to, you know, there's going to be it's going to be kind of like a bowl, I guess you could say, or something like that. Yeah, and it actually holds ice cream, or a pin top or something. All right, so a couple of things we need to know. We needed to know what the outer radius and inner radius is equal to. We need to know the intersection points. So, like, you know, I have to be able to bound my integral. I have to know this x value and this x value. And so we can do that really easy by setting the 2 equations equal. I say really easy. It just, can you solve that? Well, remember, we always want to set it equal to 0. I mean, you can look at it and see it's 1 and 0. But the math way to do it is to square both sides. And so we'd have x equals x to the 4th. And then you set it equal to 0. So you'd have x to the 4th minus x equals 0. You factor out at x. So then you get x equals 0, and then x cubed minus 1 equals 0. So, yeah, let's move that 1 over. And then we'll take the cube root of both sides. And the cube root of 1 is 1. So mathematically, that's how you find the 2 boundaries there. We need to know what the outer curve, the outside of the figure, like the outer radius will be, and then we need to know the inner radius. So the outer radius is going to give us like the volume of the figure if it had no hole. Okay? The inner radius is going to be all this stuff on the inside that I'm going to be missing. So here's a little bit better picture than what I have. I'll put up here, let you see. I may have to remove it to another page. Alright. Yeah, so like a big bowl, a contact lens, you know, it could be a number of things. Whenever I look at it, I just, you know, try to use my imagination. Call it what you want. Anyway, so we need the outer radius. That would give us the volume of the entire thing. So the outside here, the outer radius. And then we need the inner radius. You know, what would give us the heights of the rectangles beneath the figure. So our outer radius, our capital R of x, that's going to be the top curve. That's the square root of x. And our inner radius, that's going to be the bottom curve. It's going to be x squared. So now we can set up our problem. Volume equals pi times the integral from, we found our boundaries, 0 to 1, and then capital R of x squared, so that's the square root of x squared, minus little r of x squared, so it's minus x squared squared dx. Alright, so that's just going to be pi times the integral from 0 to 1 of x minus x to the 4th dx. Alright, so the integrals are easy. So we have pi times x squared over 2 minus x to the 5th over 5. And I'm evaluating that from 0 to 1. So that's pi times, plug in a 1, I get what? 1/2 minus 1/5. Now always make sure you plug in the 0 and make sure, because when I plug in a 0, I get what? 0 and 0. So 1/2 minus a 5th, it's going to be 5/10 minus 2/10. It's going to be 3/10. So 3/10 times pi. That's the volume of the figure. We're doing what we did before, except we had to change. We have an inner radius that will give us the volume of the whole figure. I'm sorry, an outer radius that gives us the volume of the whole figure, and an inner radius, we're subtracting that part out. That's why we have the minus right here.
So
But yeah.
basically, those are the things that you've done so far. One.
Yeah, the washer method is just when you're missing some inside stuff to your picture. Let's see. See if I can find one on the homework. Alright, one of these on the homework has, or at least one of them. Yeah, one of them has A, B, C, and D. Because it's just like, revolve it about this, revolve it about this, revolve it about this. And of course, the formula does change if you go from horizontal to vertical. So, if you go to a vertical axis of revolution, you want x equals y. So you got to make everything x equals y. So how about we do one like that, since we haven't done one like that. So here are our equations. These are really easy to sketch. And we want to revolve this about see. Let's make it tough. I'll do D. D is the hardest out of all of them. So part D says to revolve about the line x equals 9. A is pretty easy. B is just a little different because you got to make everything x equals y. But then C and D, you're revolving about different lines. And I think on C, you're going to revolve about this line, which makes it not so bad. But then if you revolve about a line like this, you got to be super careful when you're coming up with your outer radius and your inner radius. That's the line. All right. So, just a rough sketch here. So here's y equals the square root of x. Pretend. And then y equals 0 is the x-axis. And then x equals 3. You go to where x equals 3. Let's say 3 is right there. Alright. So it's right here. So it's not a triangle. It kind of looks like a triangle, but it's not. It's got a little curve there to the hypotenuse. But then it says about the line x equals 9. So we got 4, 5, 6, 7, 8, 9. Maybe not to scale that great, but so we're taking all this stuff in here, and we're revolving it about x equals 9. So imagine what that would look like. There'd be a lot of empty space there in the middle. I tried to imagine maybe like a volcano with a hollow center. It'd have a lot of space there, though, to be a hollow center.
I don't know why, but it reminds me of one of those like big old football stadiums. It's like have that open top.
Yeah. Yep, it could be the pit of death, where people fight to the death. Yeah, it could be that too. All right, anyway. So let's see if we can figure out the outer radius and the inner radius. Now, first off, this is a vertical axis of revolution. So when we have a vertical axis of revolution, we want x equals y. We don't want y equals x. So if I come over here and I solve this right here for this curve right here, I'd square both sides and I'd have x equals y squared. So this line that's drawn right here, this is also x equals y squared. Alright, so we need to figure out the outer radius and the inner radius. And the outer radius is going to be capital R of y. That's going to be probably the hardest one to figure out. Capital R of y. And the inner radius is going to be the missing part on the inside. So it's actually going to be pretty easy to figure out. R of y, little r of y. Now the reason why it's so easy to figure out is because the inside of the figure, that's going to be the radius of the inside of the figure. It's never going to change, you know, because this line goes up at 3. So the inner radius, how many units, if that's 9 and that's 3, how many units is between those two? 6. So that part's easy. It's finding the volume of the entire thing that makes it a little bit harder. Now remember, we're taking these rectangles here, like that, and we're revolving them about this line. Well, it's really not too bad if you think about you're trying to find like this rectangle here. Ooh, that was really bad. Because the capital R of x would give us a solid figure, and then we subtract out all this inner stuff. We subtract out that part. So all we really need to do to find that, again, let me draw it up here. It's the best way to think about it. It's like you're thinking about this rectangle here, that, whatever the height of that is, which I guess you could call it the width, but whatever the height of that is, that's the outer radius. So you would need to say right curve minus left curve. So what's the right curve? 9 minus, what's the left curve? What's the one over here? It is the square root of x, but we have to write it as y squared. So that's why that one's really hard to do. So you're going to say right curve minus left curve to get the height of that rectangle. All right. The inside, the part we're missing, it's easy to figure out because it's just going to be the same everywhere. The radius is going to be 6. Whenever you revolve that around, right, because it's going to be this big circle in the middle that you're missing, and then it's going to come, man, that's like super bad. It's the worst drawing you've ever done. Then it's going to come down, you know, like that. And you have your big pit of doom there. Let me erase that so nobody else will see it. All right. So we have our outer radius and our inner radius.
Why is it 9 minus 1 squared? Is it because we're revolving on 9?
Yes. You could say 6 plus 3 minus y squared and get the same thing. But I just went ahead and added the 6. I went all the way to the line. Remember, the capital R of y would give you the volume of the entire figure with nothing missing. The little r of y would be the missing part that you have to subtract it out. That's why in our formula, when we set up our integral, we have r of y, little r of y minus little r of y squared. Again, you could just say 6 and then plus 3. That's the right curve minus the left curve. But I just went all the way to show you. The first part, the capital R of y, if we just use this, it would give us that entire figure with nothing missing in the middle. All right, so how would I set up this integral then? So I have volume equals pi times the integral. What are my x boundaries? Or no, not x boundaries. What are my y boundaries?
9 minus y squared?
No, we're not going to have a boundary that's a variable, not until we get into multivariable calculus or Calc 4. So it's not x boundaries. It's y boundaries. And my picture's not to scale. So we know what the bottom is. The bottom is 0. We just need to figure out what this is, the top. So what does x equal? 9? What would y equal when x equals 9? Square root of 9 or 3. So that's the top boundary, 3. Remember, we need capital R of y squared you just plug in this x. You could plug it in right here, but then you'd have to take the square root of both sides and just remember it's just a positive value. Or you could plug it in right here and just take the square root of 9. It gives you the height. Remember, if we have x equals y, we have to use C and D. That's those points. This, like I said, this is probably the toughest one on the homework. All right, so we have capital R of x squared. So that's 9 minus y squared squared. I don't know why I put so many brackets there. That's okay. And then minus what? Little r of y. 6 squared dy. 81 minus y to the 4th, right? No, it's not. Got to square that. It's 81 minus 18y squared plus y to the 4th. All right. That times that, that times that, that times that, that times that. Combine the like terms, and now minus 36. I've seen students come down to this part and not combine those like terms right there. It's okay not to, but you're going to do extra work in the long run if you don't, because you're going to do 2 integrals. So you might as well just put your constants together. So 81 minus 36 is 45? No? Yes? Okay. Minus 18y squared plus y to the 4th dy. From now, let's integrate. So that's pi times 45y minus, that's going to be 18 divided by 3, 6y cubed plus y to the 5th over 5. Evaluated from 0 to 3. So pi times 45 times 3 minus 6 times 3 cubed plus 3 to the 5th, big number. And then plugging in a 0 gives you 0, 0, and 0. 45 times 3 is 135. 3 cubed is 27 times 6 is, I agree, 2, carry the 4. My brain's not working very good. Is that 162? Alright. Something just didn't look right. Alright, plus, what is not looking right? I gotta look at this for a second. I know what's not looking right. I wish I had a 3D picture of the figure because it goes like this, okay? It goes like this, and then it comes down here. So D is not up here, D is right here. Sorry, I messed up. So what X is that? It's X equals 3, but what would Y be equal to? Square root of 3. It didn't change it didn't change any of that work. It changes it right here. So this boundary was the square root of 3. I was making it really tall. And yeah, that was bad. Square root of 3. Alright. Just got to redo some calculations here. 45 square roots of 3, that's pretty easy to work out because it's just 45 square roots of 3. Minus 6. And what's the square root of 3 cubed? The square root of 3 cubed is 3 square roots of 3, right? Or is it? Then you have to say that times 6. So you plug this in right there. Square root of 3 times square root of 3 times square root of 3 is 3 square roots of 3. So then you plug it in right there and say it times 6. That's going to be what? 18 square roots of 3. At least it looks like it's going to be easier to simplify at the end because they're all going to be square roots of 3. There's no fractions to deal with. Now what about the square root of 3 to the 5th? So for every 2 you bring out a 3. So squared would bring out a 3. The 4th would bring out a 3. So that's 9. And that would leave you with a square root of 3. Is that right? 9 square roots of 3. Just gotta make sure I do that part right. Square roots of 3. Yeah, over 5. I lied, there is a fraction. That's when you just plug it out on a calculator and hit enter and get a decimal, right? So that's fifths. We have to put all that in fifths. All the numbers in front. The square root of 3's you treat like variables. So all of those are going to be fifths. So 5 times 45 is 225. I just know that from trig. So it's 225 square roots of 3 minus, 5 times 18 is 90 square roots of 3. And then, just 9 square roots of 3. Alright. So 225 minus 90 plus 9. 225 minus 90, and then this one, 35 plus 9 is 144. So it's 144 square roots of 3 over 5 times pi. That is by far the hardest problem. The other one of the other problems is just going around the line 3. Like this was part D. Part C was just going about the line 3. So it's going to be a lot easier because whenever you go about the line 3, you're making a solid figure. So since it's not going to be a washer, it's just a disc if you're just going around 3. That's what part C is. So you just say right curve minus left curve, 3 minus y squared is your capital R of y. You don't have a little r of y because there's no missing piece then, right? Because it would just be on, it would just come down on the other side. And I'm sure yours will be the same. Whatever number you have right here, your problem before, it uses these same 3 for like all 4 problems. So make sure you at least try to work a couple of those. I don't expect you to do all that homework. I do have a few more examples that I'm going to email to you that I worked out for my YouTube channel. I think it's like 4 easy examples using the shell and disk method. And look at that if you need a little extra help. So, but that's going to be it for today. This is 7.2, yes. We'll do 7.3 tomorrow.